All right. I am going to move to something that may look a trivial topic, but it's actually about this topic of latent variables is 50% of machine learning. So what I'm going to try to do, I'm going to try to demonstrate the idea with examples, and then, I will assume next Tuesday, I'm going to come back to give you some insights on how these ideas are being generalized, okay? But right now I'm going to omit actually the early slides that sort of require that you have a deeper understanding what the latent variables are, and try to demonstrate things with some simple examples. So first I want to remind you this K-means clustering algorithm, simply because the algorithm we're going to use will be a probabilistic version of what you see here. So it's an unsupervised learning problem. So I give you a bunch of data x1 to xn, okay? And I'm asking you to partition them in capital K classes, okay? So if you partition them in capital K classes, basically you're going to have to define the mean of each cluster. And usually the idea here is you're going to use this algorithm for model reduction. So if you take all of this data and you say this is cluster 1, usually what you will do is, instead of keeping track of x1, let's say x25, x50, that they're in cluster 1, you're actually saying, I am going to represent all of those points with the center of that cluster, which I call it mu1. So you can think this as a way to compress the information from the data with the corresponding mean of that cluster, all right? So this is sort of a good way to start thinking about model reduction. You want to compress information, and the way to compress it is represent the data with K clusters, and then every point in each cluster assign as a value the value of the center of the cluster. So I don't want to, there's not much really algebra, but let me just say the optimization problem that will allow us to, we have to do two things, right? We have to, if I give you points x1 to xn, and I tell you I want K clusters, you're going to have to find the centers of these clusters, and then assign for me every point to a different cluster. And those assignments are going to be hard assignments. And hard assignments means a point is not going to be 0.5 on this cluster and 0.5 on that cluster. No, it's going to be either on this cluster or in that cluster. Hard assignments. So what's the optimization problem? The optimization problem is to actually minimize this distortion measure that we see here, all right? Where a few definitions, we are looking at data points n from little n to equal to 1 to capital N, and R and K is equal to 1 if point n is assigned to cluster K, otherwise it's 0. All right? If it is 1, if we assign it to cluster K, otherwise it's 0. So can you actually start dreaming why, if you minimize this, it actually does the job? I mean, first, can you see why, I mean, looking at this, right, what would be the optimal selection for R and K? It's either 1 or 0. So to what cluster should you assign point n that its contribution to this distortion criterion is minimal? Should you assign it to a cluster that it's further down, where xn minus mu k will be huge? In that case, right, the contribution will be huge. So what would be the best choice for R and K? To assign it to what cluster? The closest, the nearest. Okay? And so that's easy, right? So we're going to assign R and K to the nearest cluster. That's what I have here. But when I write this equation, the idea is if I know the centers, right? Because to find the nearest, you need to be able to measure this distance between xn and all the centers. So immediately you can start saying, obviously, I'm going to need some iterations to be able to compute this, right? So I'm going to do some iterations. So here we assume if we knew the centers, this is what you get, all right? And now if you know R and K, you can take derivatives of this Euclidean magnitude square measure with respect to mu k, and the answer comes immediately, right? It's quadratic. So the answer comes that mu k is given immediately through the ratio that you see here, which absolutely makes sense because mu k then, it is actually the mean of the points on cluster K. And all of these points are the points where this is equal to 1. Right? So all of these points, if you average them and you divide by the number of the points, it will give you the sample mean in that cluster. Okay? So this is what the K-means algorithm is, and it is actually, nobody is going to use it for research, but the algorithm is actually used to initialize many other algorithms. So it's the first step when you try to do clustering. The first thing you do is K-means, right? You compute the assignments to clusters and the centers, and then some more sophisticated algorithm proceeds, but this is sort of a very good, decent assignment. Again, I will not discuss this in these lectures, but you notice there, it says partition in capital K clusters. And you may ask, how do you know that I have capital K, right? So there is sort of a principled way to find that. And you may say, oh, I'm going to repeat this for 2 classes, 3, 4, 5. Yes, too much work, right? So there is a sophisticated way of doing that. So if somebody is interested, you can actually, when you search, you will find nice algorithms that allow you to compute the number of clusters. Okay, so just remember, all right, remember what the K-means algorithm is, because now I'm going to move to a probabilistic version of it that, that's not what I want. I want slide 23. All right, so let me motivate this algorithm and try to do as much as we can before the lecture today. So I am going to give you data that are coming from many Gaussians, right? So you can think I have 3 different Gaussians, and I take data from each Gaussian, and I don't tell you from where the data are coming, and your task will be to go and identify how many Gaussians I used to come up with my data set, and then you have to tell me for each Gaussian what is the mean and the variance. All right? So I'm going to hide from where I produce the data, and you're going to have to go and find how many Gaussians, what means, and covariances I use for each Gaussian. So let me remind you some basic things. This is the multivariate Gaussian. Look at it carefully, okay? And I remind you, in case, we didn't do it in this course, we mentioned it many times, the formulas that you see on the bottom for a multivariate Gaussian are the MLE estimates of the mean and the variance. So if you have a number of data sets, and you're asking what's the maximum likelihood estimate of mu and sigma, it's the sample mean and the sample variance. Okay? So remember these formulas because they are fundamental for what we are doing. This is for one Gaussian. Okay, so let's see what is the problem with many Gaussians. So if you look at this picture, right, so obviously you have 3 Gaussians. So this is actually P of x given a red Gaussian, this is P of x given, let's say, an orange Gaussian, and this is P of x given a blue Gaussian. And what is that? These are the contours now of P of x, where the Gaussian, the K, has been integrated out. I don't tell you from where each data point in here is coming from. I mean, obviously, you can guess maybe these 3 Gaussians, but you don't see them because this conditional on K is not here anymore. It's P of x, it's a marginal. Okay? So, so literally what we will do in the remaining of the lecture, P of x is going to be this mixture of 3 Gaussians. All right? If you think, if you look at this point with samples, all right, from P of x, these samples are uncolored samples, okay? And they're actually drawn from a mixture of the 3 Gaussians with mixing coefficients pi k. which you can think as prior probabilities for the mixing coefficients. So this is an easy problem, right? So you know you only have 3 different Gaussians. So if you know the particulars of each Gaussian, you can take samples. You can do anything you want to. In this case, P of x is a mixture of Gaussians. All right. Now you may say, I don't believe you. Why is a mixture of Gaussian? So somehow I may have to actually derive this. All right. I'm just telling you how all these data points are being generated. Can somebody actually give me an algorithm how these blue points are going to be generated given the information that you have here and a prior probability for each Gaussian? Can you tell me how you will generate all these blue points? What would be a principal algorithm? So where I have, let's say, P1 for the red Gaussian, P2 for the orange, and P3 for the blue. So how do I generate these points?
You sample from the weights to do.
So you sample from this discrete variable to select what Gaussian you will use, and then you go into that Gaussian and say, give me a sample, right? And you don't mark them. You don't put a color and you say, oh, that thing came from the blue, that thing came from the red. No, they're all just, like that, okay? I'm just telling you, this will correspond to this Gaussian mixture. So what you just actually told me, obviously is going to be a Gaussian mixture, right? So to sample this an X, you have first to sample a component, and then from that component you have to sample from this Gaussian. So actually, another way to look at this is that this distribution here is P of x given the color k, and this is P of k. All right? And the summation k means you marginalize, you integrate k out. Right? That's exactly what we do. All right? So we already derived it into words. Okay. So the problem, the difficult problem is, again, starting with a data set and telling you, again, I'm going to lie there pretending that this is an easy problem, telling you that we have 3 Gaussians, all right? So we have 3, all right? So for you to go and compute for me the assignments of points to each Gaussian, and then for each Gaussian to compute me these mixing coefficients, the center and the variance, okay? So that's a difficult problem, all right? The idea here is, when I give you a data point, what I don't give you is I don't give you what Gaussian the data point comes. So I don't give you the coloring. And the coloring here is what we call the latent variable. So if I go back, right, to, I wrote this P of x given k, which is this Gaussian, times P of k. So k is that latent variable that somehow, since I give you only P of x, that latent variable is not there. It's hidden. It doesn't exist, it has been integrated out. But this variable k is essential because this nice distribution that you generate here comes from the fact that you have this mixture of Gaussians. They're not 3 Gaussians put next to each other, it's a mixture of Gaussians. And actually we will see, we're not going to do like a k-means hard assignment where we're going to say this point is a blue point, this point is a red. Eventually we're going to say this point is 30% blue, 70% yellow, all right? Or I don't know if there's anything left there, but we're going to do soft assignments, right? We're going to do soft assignments. Okay. So again, that's the easy problem, and this is the problem that we're given. We have this bunch of points, and you have to find out the coloring of the points, basically. That's what it is, right? You have to figure out what it is that generates these points, and maybe more than one of these Gaussians generates the points, and that's why the assignments are going to be soft assignments. Okay, So let me just go back to this picture. I want to introduce this idea of probabilistic graphical relations. So I want you to look at the joint distribution of x and z. All right, z is the coloring of a point. So this distribution, the joint distribution of x and z, is p of z times p of x given z. All right. So this, in our case, can be the red Gaussian times the probability of a red Gaussian. Right. This is my prior. And probabilistically, I indicate this with a graph that looks like this. That you have a again, the details, because this requires another course. This relation that you see here can be extracted from the graph. This is a prior on z, and then you can see from the direction of the arrow, to get the joint distribution, you need the conditional of x given z. Okay? And the reason that this area is marked means that in our problem, I have given you this data x. So x is known, but z is not known. Right? So x is known, z is not known. Now, let's talk a little bit about the representation of z. If we knew z, we don't know z, but if we knew z, for every data point, so this is data point 1, data point 2, to start with, right, if we knew, we will, let's say the point 1 comes from the red class, point 2 class comes from the blue class, etc. So we're going to have some hard assignments if we knew from where the data point comes. All right? So this is a coloring scheme. The values of the latent variable z, if we knew from where the data points come. We don't. Okay. So what I'm going to do is, I already told you that I have a conditional distribution of p of x given z. So look at this equation on the bottom and get a sense that, see if you understand it. According to my definition, zk equal to 1 means what? That the point x comes from the Gaussian 1. All right? So that's a Gaussian with mean mu1 and sigma 1. So if I knew what, that my point is in Gaussian 1, zk equal to 1, then that's my Gaussian, that's the conditional Gaussian. Okay? So think of this, again, in the context of this probabilistic graphical model. If I knew z, all right, if I knew z, it's trivial. This is just a Gaussian, if I knew z. Okay? All right, and then I have a prior on z, and I want you to look at this equation and feel comfortable with. We have seen this prior written before many times. So it's the product over all classes, in this case I have 3 Gaussians, so k1 to 3, of pi k to zk. Do you agree? Because if you take this product, how many of the pi k's, how many of the zk's you have there? I mean, either you're going to be in the blue Gaussian, or in the green, or the yellow Gaussian, or the red Gaussian. So one of the zk's is only going to be 1, the rest 0. So what are you going to pick up for p of z? You're going to pick up the prior from that class, from that Gaussian. Okay? All right. So if I put the two things together, all right, the joint distribution of x and z is given by this wonderful formula. Okay? So let's be sure we understand it, okay? I'm only looking at one data point now, okay? So I'm looking basically one point x that depends on this particular z, and I'm writing the joint distribution like this. I mean, where did pi k to zk comes? It comes from this prior, and where p of x given z comes, you remember, if I know that z1 is equal to 1, what do I supposed to have as a contribution here on the right hand side? If I know that z1 is equal to 1, what should I have here? What Gaussian should I have? If I know that z1 is equal to 1, what is this gives me? It gives me what Gaussian? it gives me basically n of x given mu1 and sigma 1. That's the first Gaussian. I mean, if I know that my point comes from the blue Gaussian, right, then the likelihood of p of x given z is the blue Gaussian. And by having this product, I can nicely pick up all of them, because for a given point x, from the corresponding z's, only one of them is going to be equal to 1. The rest 0. I just don't know which ones are going to be 1s. Right? If I knew, right? And that's why here I write the joint probability. So P of z is the prior. And now if I knew, because this is the conditional, if I knew what z is, P of x given z will be the product over little k of these Gaussians to zk. All right? Now, you have to believe me that if you take this joint distribution the way that is written there, and you marginalize z, so you integrate for all possible values of z, what actually you get out is that P of x is a mixture of Gaussians. So can somebody highlight for me, when I say we will integrate z out, how many possible values the z can take in our problem for one data point with 3 classes, 3 Gaussians? What are the 3 possible values z can take? 1, 0, 0, 0, 1, 0, 0, 0, 1. So if I take the values of z to be 1, 0, 0, what will this thing give me? Right, so I'm going to sum for all possible values of z. If z equal 1, 0, 0, what do I get from this term?
Gaussian 1.
Gaussian 1 times pi 1. Okay? And then Gaussian 2 times pi 2. And then you get the Gaussian mixture. So the Gaussian mixture, which is obviously a complicated distribution, comes from something rather simple by integrating this latent variable z. So effectively, you can actually think that we're generating data, right, from these 3 Gaussians, but these data are somehow correlated because of some hidden cause. And what is the hidden cause here from where the data are coming is basically this z variable, right? And so you don't really see it when you look at the Gaussian mixture, but this Gaussian mixture, it requires a marginalization of this hidden cause z that connects the data x. So the idea here is, by having these hidden latent variables, you can actually generate very interesting distributions that are very useful, right? So a Gaussian mixture is, let me just say, with a Gaussian mixture I can represent anything you want to. Anything. Right? So you can give me any data set. With a Gaussian mixture, I can represent anything you want. Unfortunately, in many computations, that would not be an easy thing to do. Right? It's not that people are not trying and they have made this to work, right? But the Gaussian mixture is powerful. If a Gaussian is powerful, a Gaussian mixture is way more powerful. All right? Okay. So I haven't really solved anything, right? I introduced what z is, and I just pointed here that if we knew what z is, the joint distribution is a very nice form, right? A very nice form, but the marginal is not a nice form. Let me just tell you why it's not a margin. It's not a nice form. Let's say that you want to compute the parameters to maximize the likelihood, which is coming. If I take the log likelihood of this, what form the log likelihood we have? Log, and inside the log, what are you going to have? You have summation over these Gaussians. That's not nice. So actually, if you have lots of data points, you're going to have a summation over the data points of log of a summation over the possible Gaussians in your model. So this is going to be inside the log. If you take the log of this distribution that is the joint distribution of x and z, do you have log of a summation over the different components? No. Why? Because when you take logs of this, what do you get? You get zk times log of each of those terms separately. Can you see that? When you take logs here, you're going to have zk times log of each term separately. You don't have log of the sum of these terms. Right? You don't have log of the sum of these terms. Okay. So let me introduce now a variable using Bayes' rule, okay, that will make things interesting. So, you know, we started with a prior assignment. We said this is the blue class, this is the red class, etc. Now, I want to introduce something that is a posterior distribution. And so I want to introduce this distribution here. So can somebody tell me with words, what does this distribution says? So I give you point x, and what does this distribution says? So I only give you 1 point, right? And it says, what is this is the probability of zk equal to 1 given x. So this is the probability that the point x belongs to what class? Okay. To class k, all right? So this is the probability that this point belongs to class k. So let me do the Bayes rule. So what I'm going to do is I'm going to write this as the prior times the likelihood, all right? And then the normalization factor. Now, this likelihood says I am already in the k Gaussian, so the likelihood is this Gaussian that you see here. And what is this? Is basically the prior pi k, and the denominator is the summation basically of the numerators for all possible values of k. Okay? So this distribution that you see here, that somehow I inverted with Bayes' rule, is called the responsibility, and the word responsibility is used by Bishop to basically describe the physical meaning of what this is about, right? It says, my Gaussian k, how much responsibility it takes to explain the data point x? So you can guess, by the way, if I give you a point x and you compute this, this is not going to come to be 1 and 0. It will never be 1 and 0. So it will be a number between 0 and 1. So that's why you want to say each of these Gaussians, how much responsibility it takes to explain point x. And you can actually see, if you sum these responsibilities for all possible values of k, the sum comes to be equal to 1. It better be. All right? So effectively, each point will be explained in part by each of these Gaussians, right? Without doing hard assignments the way that we did with the prior model. So let me explain this with colors. These are the hard assignments, right? Red, blue, yellow. This is no colors at all, right? It's just data from the Gaussian mixture. And this is a coloring where I am colorblind, okay? I cannot see the differences, but still I can actually see some weird things in between. So how is the painting of this third picture comes about? Every point has a coloring that's a mixture of 3 colors. And what are the mixture components? These responsibilities. So you say you can actually go in and plot something and at each pixel put 3 colors? Yes. And it's a good idea to learn how to do that, right? So the idea is you can see the gradient, if you like, of the color assignments, right? It's all blue here, suddenly blue becomes a little bit orangey, then very much orange, and then a little bit reddish, and then all reddish, okay? So that's nice. All right. I mentioned a fundamental problem with working with Gaussian mixtures, but somehow if you compute the log likelihood, so if you have n data points, all right, the likelihood for each of the data points is this mixture of Gaussians. So you're going to have log of this sum. That is computationally intractable, right? So you're going to have summation over data points, log, summation over the components, okay? Now, we can actually do algebra for this course, right? But you can start generalizing that in many cases this will not be something that will work. So, we will have to actually do something more efficient than that, and more and easier. I don't know if I should explain this picture, so I'm going to bypass it for now. So we're going to have to address the maximum likelihood estimate for the parameters for the Gaussian mixture. In some sense, I already told you that the posterior responsibilities will do the assignment of points to the different Gaussians. That's nice. But before we do the MLE problem, let me just tell you there are issues. The MLE algorithm may not work at all. They give you garbage. So let me just give you one example. So you are looking for Gaussians, right? You're looking for a mixture of Gaussians, and for each Gaussian, you're looking for components. So let's say that I give you some data points that you see here. And let's say by accident, one of the Gaussians that you're computing has a center to be one of the data points. So let's say that one of the Gaussians has a center, one of the data points. So when you compute this Gaussian at the point xn, this Gaussian looks like this. You agree? So if one of the Gaussians is on the top of one data point, all right, you get something like that. And then remember, what is maximum likelihood, right, is to maximize the likelihood. So you are looking basically for the parameters that maximize this, and somebody will say, yeah, I found it. Take the variance to go to 0, right? Make this a delta function. That's the answer. Can this happen? Yes. And that's why when you see implementation of algorithms for these Gaussian mixtures, if this happens, basically you have to do something in your algorithm and say, forget where you are, reinitialize this Gaussian, and start again. Because if the algorithm identifies a situation like that, it will actually keep going and going and give you, I mean, if you want to maximize the Gaussian, there will be a Gaussian on the top of every point with 0 variance, and that will take the likelihood to infinity, and you're done. Right? You don't want that. Okay. There's another problem. So we said we're going to identify, let's say we have 3 Gaussians, red, blue and orange, and we call this Gaussian 1, this Gaussian 2, this is Gaussian 3. But don't you think if I take the naming of these Gaussians and I interchange them, so when you go and compute mu1 and sigma 1, that can be the blue, can be the red, can be the yellow. There is an issue of identifying which is what here. The identification basically of these 3 Gaussians is not unique, right? You can actually come up with k factorial equivalent solutions. Now you may say, you know what, I computed 3, so this is it. Yeah, but mathematically, how would your algorithm actually know somehow when the algorithm is trying to compute the maximum likelihood estimation, how is actually capable to navigate from the fact that there are k factorial equivalent solutions? I mean, think if you have 3, Gaussian 1 can have 3 colors, right? Gaussian 2 can have then 2 other colors. And then, so you have 3 times 2 times 1, that's 3 factorial. It sounds a trivial problem, but it's actually a serious problem with this type of mixture components. All right. It's 1:44, okay, so I'm going to stop there, and the discussion will be continued on Thursday. Let me just say, this algorithms, even though we use the mixture of Gaussians as an example, the paradigm is very general, so the algorithms that you will hear are applying to many problems with hidden variables, so don't think that this is a Gaussian mixture problem, and even if it is, I'm just telling you that the Gaussian mixture problem is extremely fundamental. It actually, with the Gaussian mixture problem, again, you can represent anything you wish to. All right, so I'm going to ask Nick Geneva to give the lecture on Thursday because I'm going to be out of town. So he will continue on the slides. And I apologize, I have the website with Wix, I cannot do anything about it. There is an issue which I don't know what it is, I cannot even touch it, okay? So may I recommend that you just keep looking at the slides from last year, and there is really no major changes from what you see on the slides this year. Okay, and I remind you that there is a homework due for those who have not submitted. I reminded some others last lecture, and they disappeared. So please don't disappear by me saying there is a homework due yesterday, right, or last week. Okay, so I mean, my intention is to come here and give a lecture to myself if it is necessary, but there is a homework, there are homeworks overdue. All right, so now I have to run to the airport.
Is there no lecture Friday as well?
So I asked actually Nick, because I don't want to interrupt his, he won't be able to finish it. So I told him to make a decision on Thursday, depending on how he goes. I don't want him to accelerate and cover everything in 10 minutes, So, okay. But he will continue on the same set of lectures, lecture notes on this Gaussian mixtures and the EM algorithm.